Hi everyone. I want to record a quick video on how to use a quadratic regression. So without further ado, that's what I'll do. I'm going to share my screen here real quick. And you should at this point be able to see Excel. So that's where we're going to be. We're going to be in Excel. And before I show you any data or show you how to do anything, I want to talk about when is it okay to use a quadratic regression instead of a linear calibration model. And I want to start with when it's not okay to use a quadratic regression. Okay, so when is it not okay? So when the main thing that you can't do is you can't shop calibration models. So you can't use a quadratic regression when you're just shopping calibration models. So what this means is you'd be like, try one calibration model. So try an average response factors, see if it works. Then if that doesn't work, try a linear regression, see if that works. Then if that doesn't work, try a quadratic regression, see if that works. So you can't just try different things and whichever one suddenly passes, that's the one you use today. That's a sort of a big no-no. That probably means you have bad data and you need to go fix the source of the data and not just shop calibration models. It's also, you shouldn't be using this when it's not clear that it has that quadratic shape. So it should be a curvature around a line. So it should start above the line, dip down below a straight line, and then go back above the straight line. And you'll see this in a second. So if you don't know what I mean by that, I'll show you in a second. So it should be clear that it actually takes a quadratic shape when you want to use it. All right, so when is it okay to use a quadratic regression? So when it's clear that your data has that quadratic shape, and that quadratic shape is from an instrument or analysis where this is known to occur, that's a great time to use a quadratic regression. You shouldn't have any second thoughts about it. If it has that shape and you know that this happens on this particular instrument, especially if you even know why it happens on this particular analysis or instrument, then that's great. Use it. Perfect. Generally, you also need to get permission from your supervisor to do this or for someone in the data review chain above you, because it needs to be clear that you're not just shopping calibration models. So you can't just throw it at the wall and see which one passes today. So generally, you want to just check with your supervisor that that's going to be okay to switch to that model. And as well as you need at least 5 data points. I realize I have a typo here. You need at least 5 data points in your curve to be able to properly model that shape in a quadratic regression. 6 would be even better, but 5 is sort of the minimum data points in a curve to apply a quadratic regression. When is it questionable? When should you be like, I don't know if this is a good idea or not, whether I should go with this? And that's a situation, and that is the one that we're dealing with on our GC right now, which is precipitating this. When you're using for it to account for a probable instrument problem where you should just be doing maintenance on the instrument and fixing the instrument. So this situation kind of fits where it's clear that we have a quadratic shape and we know it happens from this instrument. So it's what we expect. But the reason it's happening is because there's some maintenance probably that I need to be able to do, even if I don't yet know what that maintenance is. It's probably the cause of some maintenance that I need to do on this machine that will take away the quadratic shape. So then it's questionable. You can go ahead and do this, but really you should be taking the instrument offline, fixing the problem, and bringing it back online with the original linear shape. And I'm trying to do that right now, but haven't solved the problem. So we're going to use it for the time being. Okay, so without further ado then, let's go over here to our data and see how this would play out. So let's just grab this data and put it on a graph. So we'll start out by just showing you what we're talking about, looking at it as if it were linear first. So I've got some data here. These are just made up concentrations. I don't have a unit because that doesn't matter at this point. And then this is the response from the instrument. I'm going to highlight that data. I'm going to go insert a scatter plot right here. Put that right there. So just glancing at it on the graph, there's nothing, obvious about it at all. So we're going to go ahead and insert a trend line, and we'll just go ahead and use the linear trend line to begin with, and we'll put the equation on the chart and the R squared value on the chart. And so you can see that this is really not, it's not the worst thing you've ever seen, but 9948 is generally not going to be slightly below passing for linear. And you can actually see why that shape of the data here, it starts above the line. This one's not the worst ever data, so I haven't made this unbelievably pronounced. This is what your data probably will look like, where it starts above the line, and then it dips down below the line for a couple standards and then comes back above the line for your final standard. So you need to see that where the first one or two standards are above, it dips below the line for one or two, and then it comes back above for the end. That shows you that there's a curvature of this graph. And if we switch this trend line then to a quadratic, you'll see the issues here. So we go to quadratic means a second order polynomial. So instead of y equals mx plus b, it's going to be x squared term and an x term and then an intercept term. So when I put that on there, you can automatically see, you can see that when that curvature applies, that it hits all the data points really neatly. And you get all of a sudden a very, very beautiful r squared value. And you can see that the equation has taken the quadratic shape, ax squared plus bx plus c. So that's it. We've done our quadratic regression. We can see the quality measure, which is r squared, would be passing by most standards. Generally, it's like 998 or something like that, is good for a quadratic, which every situation might be a little different. So check your procedure for that. All right, so this is great. So then how do we use this to calculate data? So the first thing I'm going to suggest is that you switch what's on your X and Y axis. Your calculations will just go a lot easier and they'll work out to give you the same numbers ultimately overall. So to do that, I'm going to come in here and select data, edit this cell. And there's a few ways you can do this, but basically you can see sheet 2 here, or X values here are A2 to A6. And we want that to be the B value, the ones in column B instead. So you can do it a couple different ways. I'm just going to highlight this here. Nope, got to get rid of the old data and then highlight this here. And then we want to switch to the y-axis being the ones in column A. So you can see what happened when I get out is we've got, there is a little bit of a difference here in the r squared. And you've got this sort of different curvature in the graph, but this is a nicer way to do it for a lot of reasons, but ultimately it'll just make your calculations a lot easier. So you want to do it this way, but still looks really, really clean. We did call ourselves a problem though with my set of data, and these terms don't only have one sig fig, this one, and same here. So we need to get some extra digits one way or another. The easiest way to do that probably first is to find in your label, oh, I was there, where it says the number category, and switch it to just a number and tell it how many decimal places you want to see. So you might try something like 5. If that's enough, that doesn't look like enough for me. So I'll go to 7. And that looks like it'll probably work, although I'll need to move it a little bit. So I'm not able to see this up here because this term is very, very tiny. So I'll drag that over here. And I'll keep going. Hopefully this will work. So this data I made up turns out to be kind of annoying because it's giving me some lots of decimal places here, but that's fine. This will be a number that's relatively easily usable, and we'll go from there. You could put it in scientific notation, I believe, but this, yeah, you could go into scientific notation and then you could see it differently, but it doesn't really matter, your choice. All right, so then how would we use this? My first thing I'm going to recommend, as always, you could take these off this, like take these numbers out of the graph and use them directly to do your calculations. But what I'm going to recommend is using this formula that will give you these, but we'll check them against the graph to make sure we're calculating it correctly. So that formula is called line ST, LINEST. You can see it come up here. And you're going to put your known y's and your known x's, and then I'm going to give you a special little trick so you can make this a quadratic regression instead of a linear regression. So first we'll put in our known y's and x's. We can see that the response is on the x-axis and the concentrations on the y-axis. So for my known y's, I'll just highlight that column, then comma, then my x's. Then what you're going to do is you're going to click raise the power of curly brackets 1, comma 2, close curly brackets, close parentheses. I think this is correct. We'll see here in a second. When you hit enter on this, it'll give you all three of those terms. This one should match here. Negative 2.275 times 10 to the negative 10 is this one, the A term. 0.0081 is the B term, 0.00081. Except that I don't have enough decimal places, so I'll increase out some decimal places here. And then negative 4.61249 is the C term. So this is your equation in the form of y equals ax squared plus bx plus c. Those are your terms. So how do you use this to calculate it then? If you want to calculate the concentration then of this unknown, y is concentration. So you're just calculating y. So you say equals A times X, the response, squared, plus B times X plus C. Enter. And you can see that this then calculates out as a concentration of 229, which is in our curve. 318,000 is a little bit less than 352,000. So we would expect somewhere a little less than 250. And you could plot it on your graph too, so you could see that it's calculating correctly. 318,000 would be somewhere here, plot up to the line, plot across, and it looks like, yeah, 230 is about right. So that's calculating correctly. We're pretty much set. There's one thing I didn't do, which you will want to do if you're going to do this for more than one sample, and that's go back to that formula, and the cells here, A15, B15, C15, you want those to be hard references. So click on in the formula bar up here, if I don't know if you can see where I'm at up here, in the formula bar, and click anywhere near A15 and hit your F4 key, and that'll add the dollar signs to those terms so that when you copy and paste that, it'll always refer to those three cells. And that's it. That's how you do a quadratic regression. Hopefully that helps.